Okay, as you can see, we're going to take a look at inverse matrices today, and they definitely have their place in the real world, although you may be left with some questions about that at the end of this. This is primarily going to be mechanics. So let's take a look. Okay, show that A and B are inverse matrices. Well, what we know about inverse, and when they're talking about inverse, they're talking about multiplicative inverse. We know multiplicative inverse, for instance, 5's multiplicative inverse is 1/5 because 5 times 1/5 is 1. Well, in 2 by 2 matrix land, 1 is this guy. So that is 2 by 2 matrix land's version of 1. You can check that real quickly by just multiplying, for instance, matrix B times that matrix, and the result just stays matrix B. So it's kind of like taking 5 times 1, we just get 1. So to show that A and B are inverses, we need to take matrix A times matrix B and see if we end up with 2 by 2, the equivalent of 1. So let's go ahead and take a look at that. So I'm just going to repeat matrix A, 1, negative 1, negative 1, 2 times matrix B, 2, 1, 1, 1. And I'm assuming you have some background in multiplying matrices at this point. So when I take matrix A times matrix B, my first entry is going to be this 1 times this 2 plus this negative 1 times this 1, 2 times 2 plus negative 1 is 1. My first value is 1. I should write these really as matrices and not as determinants. And then continue on from those values. When I take this 1 times this 1 and add to it this negative 1 times this 1, I get 1 and negative 1, 0. Then next step would be to jump down to row 2. I'm going to take this guy times this guy and add to that this guy times that guy. So negative 1 times 2, negative 2, plus 2 times 1, 2, negative 2 plus 2, 0. And then finally, I'm going to take this times this and add to it this times this, and I get negative 1 plus 2, 1. And I see, yes, in fact, we did arrive at this. What would be left to do then, because what we've learned about multiplying matrices is matrix A times B is not necessarily equal to matrix B times A. In fact, if I can multiply matrix A and B, that's no guarantee I can multiply B and A. However, I can if the matrices are squared. So what would be left would be to show that this works as well. The product of matrices is not commutative. So we have to test both ways according to the book. We'll come back to that. So we go through this process and we end up finding out, and you can do this one, we end up finding we're here. So at that point, yes, we have shown that A and B are inverses. But I am telling you, yes, the product of matrices is not commutative. However, a square matrix times a square matrix that gives us 1, in this case 2 by 2 land, that would be commutative. I'm claiming that you only have to show that that works one way. Okay, let's move on. Now, finding inverse matrices, there's what I think a really lousy way to do this, but it should make some sense. And then there's maybe a more tougher to understand why it works method, but trust me, it works. So here's the not so efficient method by hand, in my opinion. We know that if matrix A here has an inverse, then 1, 2, 3, 7 times some 2 by 2 matrix, let's say the values are A, B, C, D, would have to equal 1 in 2 by 2 land, which of course is 1, 0, 0, 1. So what do we get when we do this matrix multiplication on the left side? I get 1A plus 2C and then I get 1b plus 2d, and then I move to the second row and I get 3a plus 7c, and I get 3b plus 7d. And what do I know about those values? I know this guy has to equal 1. I know this guy has to equal 0. And I know this guy has to equal 0. And I know this guy has to equal 1. And then I've got two different 2 by 2 systems, and then we can solve each of those through elimination. Okay, great. Now, just imagine what it is as a 3 by 3. Here's another method of doing that. And hopefully this first method, it makes sense. We could figure out A and C here. We could figure out B and D here. Should make sense. Then we just patch that back into this matrix, and that is our inverse. But here's an alternative. May not make as much sense, but I think it's just a lot simpler by hand. So I'm gonna rewrite my matrix, and I'm gonna augment that, add on to that, the 2 by 2 version of 1. And now I'm going to Gauss Jordan this guy and turn this into that. And the values on the right, the 1, 0, 0, 1, just kind of go along for the ride. So I'm going to use 1 to whack this 3. I'm going to multiply the first row by -3 and send it down. First row stays 1, 2, 1, 0, and I get -3 and 3, 0. I get -6 and 7, 1. Ooh, that's convenient. I get -3 and 0, -3, and I get 0 and 1, 1. So now I'm going to use this 1 to whack that 2. I'm going to multiply by -2 and come up to that neighborhood. So I get 0 and 1, 1. I get -2 and 2, 0. I get +6 and 1, 7. I get -2 and 0, -2. Now, normally in the Gauss-Jordan process at this time, we'd be looking at dividing this row by that value and dividing this row by that value, but they just happen to be 1s. So our inverse is what remains. This is our inverse function. If this was matrix A up here, A inverse we would write is equal to 7, -2, -3, 1. And by all means, be my guest, go through that process. Well, that's what we should end up with. Okay. All right. Let's move on. Find the inverse. We would go same exact process here. 1, 1, 1, 3, 5, 4, 3, 6, 5. I'm going to tack onto that. Now, fortunately, our calculators do this for us, but I'm going to go through this process. You can see a 3 by 3 Gauss-Jordan. I'm going to use 1 to wipe out those values. So I'm going to multiply by -3 and add it into both rows. Okay, I have some previous videos. If you go to the 7.3 section, there's a video on doing Gauss-Jordan 3 by 3s that slow down a little bit. I'm going to go through this pretty quickly. First row is going to stay the same. 1, 1, 1, 1, 0, 0. Of course, I augmented this with our 3 by 3 version of 1. Okay, row 1 into row 2. Row 1 times -3. That gives me -3 and 3, 0. -3 and 5, 2. -3 and 4, 1. -3 and 0. 0 and 1. 0 and 0. -3 times row 1 into row 3. -3 and 3, 0. That's why we're doing it. -3 and 6, 3. -3 and 5, 2. -3 and 0, -3, 0 and 0, 0, 0 and 1, 1. Okay, next step. New hitman, taking care of this and this. I'm going to multiply this first row by -2 and go pay a visit. I'm going to multiply this row by the second row by 3 to get a 6 and go visit this row times -2. Okay, I think I have room to fit that down in here. So I get new matrix. Let's go row 1. I'm going to multiply row 1 times -2 and add row 2 into it. I get -2 and 0. I get -2 and 2, 0. That's why I'm doing it. I get -2 and 1, -1. I get -2 and -3. I get 0 and 1. I get 0 and 0. Second row stays the same, 0, 2, 1, -3, 1, 0. And third row, I'm going to multiply second row by 3. Third row by -2, add those together. I get 0 and 0. I get 6 and -6. That's our purpose. I get 3 and -4, -1. I get -9 and +6, -3. I get 3 and 0, and I get 0 and -2. Okay. At that point, I'm to my next step, where I'm going to use this -1 to get rid of those guys. So I'm going to multiply this by -1, send it up to here, and I'm going to leave it exactly as it is and send it into there. So we end up with first row plus -1 times the last row. I get -2 and 0. I get 0 and 0. I get -1 and +1, 0. That was our purpose. I get -5 and +3, -2. I get 1 and -3, -2. And I get 0 and +2, 2. Second row, just adding the third row into it, I get 0 and 0. I get 0 and 2. I get -1 and 1. That's why we're doing it. I get -3 and -3, -6. I get 3 and 1, 4. I get -2 and 0, -2. Last row at this point stays the same. 0, 0, -1, -3, 3, -2. Okay, here I'm going to divide the first row by -2, divide the second row by, that's kind of backwards, divide by -2, divide by 2, and divide by -1. So I end up with +2, 0, or excuse me, +1, 0, 0, +1, +1, -1. I end up when I divide by 2, 0, 1, 0, -3, 2, -1. And when I multiply or divide by -1, I end up with 0, 0, 1, 3, -3, 2. So I have now made this side look like that side. Therefore, this is my inverse. Isn't it nice that we have calculators to do this for us? Imagine a 5 by 5. Okay, use the inverse matrix from number 17. So I need that inverse matrix from 17. So you can go back a slide if you want to see where this came from. We can back up, take a look at this guy. I'm just going to copy that down up here. So the values from that are 1, 1, -1, -3, 2, -1, and 3, -3, 2. That is our inverse coefficient matrix. And now, what you might note if we go back to the previous slide, take a look at these values, 1, 1, 1, 3, 5, 4, 3, 6, 5. 1, 1, 1, 3, 5, 4, 3, 6, 5. 1, 1, 1, 3, 5, 4, 3, 6, 5. That's why we're using that inverse matrix to solve this. Now, you're going to hear me say this a number of times. Using an inverse matrix to solve a system of equations is a lousy way to solve a system of equations. But there are some exceptions to that, and we'll talk about that in a bit. So what the intent is we would set this up as this system up as the product of matrices, and that can be set up as this: 1, 1, 1, 3, 5 for our coefficient matrix, our matrix A, 3, 6, 5, times XYZ. If you take a look at that, the product of that gives us exactly this, equals -1, 2, 0, this matrix, which I'm going to rewrite that and give myself a little bit of room for some explanation here. So I'm going to put that over here as -1, 2, 0. Now, if we were solving this equation, 4x equals 7, we would divide both sides by 4. Alternatively, we could multiply both sides by 1/4, and we get x equals 7/4 either way. Now, we can multiply by 1/4 because 1/4 is the multiplicative inverse. If I take my multiplicative inverse in my matrix here, multiply this side by it, and this side by my multiplicative inverse, my equation becomes plain old XYZ, because these guys cancel, equals A inverse, which happens to be 1, 1, -1, -3, 2, -1, 3, -3, 2, times -1, 2, 0. Let's see if we can do that one in our head. So I'm taking this, this, and this times this, this, and this, etc. I get -1 plus 2, 1. -1 plus 2, 1 plus 0, I get 1. For row 2, I get -3 times -1, 3. 2 times 2, 4. 3 plus 4, 7 plus 0. And for row 3, I get 3 times -1, -3. Plus -3 times 2, -6. That's -9, and 0. So there is x, y, and z. Again, awful, awful way to solve this system. If I had to do this by hand, I would just Gauss-Jordan that guy. I mean, that Gauss-Jordan is easier than the Gauss-Jordan we did just to get to there. And then we still, after we got to the A inverse, we still had to go through this process. So, lousy way to solve a system of equations, but it still has its purpose. Okay, this is a problem. I'm going to put the problem just like this on the test, and I'm going to word it in, for 3 different things for you to do. First is going to say rewrite the system of equations as the product of matrices. So that would become 18, 12, 30, 24 times matrix XY equals 13, 23. And you get 5 points just for that if you're taking my test. And this we're going to call matrix A. This is big matrix X, and this can be matrix B. A very common naming convention for this. Okay, that's the first part. Part 2 is going to say find the inverse of matrix A. Show that this was done by hand. So we're going to do the Gauss-Jordan thing. 18, 12, 30, 24. Attach our 2 by 2 equivalent of 1, our identity matrix, and Gauss-Jordan this. Yuck. 18 and 30 match up at 90. I need a 90. I've got a 90 now. I need a -90. I've got a -90. So step 2, I get 18, 12, 1, 0. I get 18, 5, 90. 30, -3, -90, 0. I get 5 times 12, 60. I get 24 times -3, -72. I get -12. That's going to be very convenient. I get 5 and 0, 0. I get 0 and -3. Oh, I'm sorry. I think I did that earlier too. I get 5 and 0, 5. I get 0 and -3, -3. Now I need to use my -12 to wipe out this guy. How convenient. I can leave it as it is, send it up. and I get 18 and 0, 12 and negative 12, 1 and 5, 0 and negative 3, and all that's left is divide this row by 18, divide this row by negative 12, and I've got my inverse matrix because I get 2 here. 1, 0, 0, 1. 6 on 18, 1/3. Negative 3 on 18, negative 1/6. 5 on 12, on negative 12, negative 5/12. And negative 3 on negative 12, positive 1/4. There is our inverse function. If I took that inverse function and multiplied it to both sides, I would end up with x on y equals, in this case, this would be a inverse, 1/3 negative 1/6, negative 5/12, 1/4 times 13, 23. Now the second part is just to get to here. So first part 5 points right here. Second part 5 points, find the inverse by hand. And third part we'll say use the inverse matrix to solve the system. So that's what I've started doing right here. Well, that becomes, and it's a little ugly for a moment, xy equals, do your matrix multiplication. That's 1/3 times 13. 13 thirds plus negative 1/6 times 23, negative 23/6. Row 2, negative 5/12 times 13, negative 65/12, plus 1/4 times 23, 23/4. Or, if I convert this to sixths, both denominators to sixths, I get 26/6 minus 23/6, or 3/6. In the denominator, if I go to twelfths, I get negative 65/12 plus 69/12, 4/12. Or x is 1/2, y is 1/3. 5 points for doing that. Now, I've mentioned a few times that solving a system by inverse matrices is a lousy way to solve a system, and I think you're pretty convinced of that by now. Wow, that's a lot to do for what's normally a pretty simple rote process for us. Let me jump back to this ugly page right here. Let's assume for a moment that we have some working condition, some situation arises, and we could go through a number of cases like that, where this side of this system always stays the same. The only thing that changes is the values we have over there. And let's say we had to do that 100 times a day, but matrix A never changed. Only matrix B right here changed. And if matrix B changed, all we would have to do is use matrix A's inverse right here, and we would just have to change these values, those 3 values, and doing that in a spreadsheet is incredibly efficient, and much more so than going back in and RREFing in your calculator over and over. So here's the deal. Solving a system of equations using an inverse function or inverse matrix is a lousy way to do it for a problem. But if you had a whole bunch of problems where matrix A values always stayed the same and matrix B was all that changed, then it is a great way to solve multiple systems of equations. Hope that's helpful for you. Stay tuned. We're going to soon, if you just happen upon us at YouTube, you can follow along with us at purpleshirtednerd.com. This is the chapter 7. I believe this is 7.6. Or this is, yeah, 7.6. We're going to have more examples of using inverse matrices to follow in section 7.8. So stay tuned. Hope that's helpful, and good luck.